Hello guys, in this video I'm going to talk about the k-means clustering algorithm. So we have seen the Bayesian decision rule till now, and what we have seen in it is mapping Gaussians. So say this is my data. So here I am considering a two-dimensional data. So here there are two features x1 and x2. So as our previous videos, we have taken s1 as say size of the flower that we are classifying, and x2 is the luminance of the image of the flower, right? So we considered three flowers: sunflower, rose, etc., and we are plotting its data over here. So here x-axis is telling the size, what is the size of the flower from the radius, and the y-axis is the luminance. Right, so suppose this is the data that we have. So what will Bayesian rule do is it will try to fit a Gaussian to every data. So say if suppose this is data for rows, so it will try to fit a Gaussian like this. So there will be a Gaussian like this that will be fitted. So remember when I talked about my multivariate Gaussian case, there I told you that in 3D, because we cannot visualize everything in 3D, what we do is take the top view, and from the top view we see the Gaussians as an ellipse. So similarly we'll get an ellipse over here for this class, and there will be a Gaussian over here. So if you see here, there is a problem. This is okay, this is far apart, so these are okay, but here there is a problem. Both of these classes are overlapping. So actually if you see, the classes are not overlapping, but the Gaussians, the probability distribution that we have fitted over them, they are overlapping. So this is a problem with the Bayesian decision rule, and not the Bayesian decision rule, but the Gaussians that we are assuming. We are assuming that the likelihood is Gaussian. This is making this kind of problem over here. So then there could be a better way of doing this. So here please note that a class is divided, you can see clusters are forming in a particular class. So all these, say they belong to sunflower, suppose. So this may be smaller sunflowers, they have smaller size. So here you can see their size is small, so there are smaller group of sunflowers and some larger sunflowers over here, but they are well clustered. So then there came an idea, what if instead of fitting just one Gaussian, we fit two Gaussians like this. So instead of just fitting one Gaussian on the whole data, if we can fit two circles or Gaussians, it would be so nice. So there will be a circle like this for every particular class. So this is what is k-means clustering. What we do is we try to cluster the data of the same class. So here these two, both of these what we call circles are belonging to sunflower. Both of these circles are belonging to, say, some flower, and both of these, say, are belonging to rose. So instead of fitting only one Gaussian on the data, we try to fit two. So now this may be Gaussian, this may be something else. Now in k-means clustering, we don't assume Gaussian, we just take the distance. So we'll see what happens in k-means cluster as follows. So this is the basic idea of the k-means clustering. Instead of fitting a whole thing, you fit small two things and you can get good results. So here you can see, if I fit this like this, you can see that there is very less overlap now. Here the problem of overlap is almost gone. So that is the beauty of k-means clustering algorithm. But this algorithm has a problem. The problem is such that if suppose this is a data of say sunflower, so I'm just taking one class at a time. So here say I have taken just the data of sunflower. So now for the algorithm, it is very difficult to identify which sample should go to which Gaussian. So you can see this very nicely, and you can take a circle around it. That is very easy for a human, but for a machine these are numbers. Remember, these are as vectors. So there is a big list of vectors having x1 x2 coordinates, and you have to find out which particular data is for which Gaussian using this. So this is like a very difficult task, because uh, first of all you need to know what is the mean. So you should, so basically how do you start the algorithm, from where will you start, which sample will you take? So hence there is little difficulty while choosing the k-means algorithm. So what we do is we so the algorithm is as follows. What we do is we select some initial choice of means. So this algorithm is called k-means because there will be k number of Gaussians, or k number no, Gaussians is the wrong word in k-means. So k number of circles that will be allotted to one data. So here as you can see I have allotted two circles for a data. So like this you can allot k circles. So for the k circles there will be k means that we will have to calculate, and that mean will tell you how the circle's position. So let us see what the algorithm is. So there are going, so initial select the initial choice of, okay, there is a small mistake, initial choice of k means. So you have to select k means. Now this k is a thing that a developer decides. So this is a, so now actually for the data to decide how many Gaussians to fit is one more difficult task. So data cannot decide, data what, the algorithm cannot decide how many circles to fit. So we choose an initial value of k. So let me visualize it to you what is happening. So what am I doing is I am choosing any random initial value of k. So here I am using k is equal to 2, hence I made two means. So here you can see the algorithm is select initial choice of k means. So I am choosing two k means. So basically this is one mean and this is two mean. So this mean will correspond to a circle and this mean will correspond to the other circle. Also please remember I am just using class sunflower. There is only one class over here. These are not two other classes. This is just one class, sunflower. Right. So I have randomly chosen any point as the mean over here. It is totally random as for now. Now next you have to determine which sample belongs to which cluster. So according to this mean that I have, now I will choose which sample will belong to which cluster. These means will basically form the cluster, and we have to choose which particular sample will be in which cluster. So according to this arrangement, it is very intuitive that the samples near to the mean will get grouped in that particular means cluster, right? So say suppose there is this sample over here, so this sample will get mixed with this mean. I'm denoting this mean as say black color. So you can see the distance of this sample from this mean is lesser than this mean, hence I chose this. So because you can see if there is a cluster over here and the mean is here, so the points are close to the mean, right? So that is the thing that I am using over here. So initially I have chosen a random mean, and now I am allotting points to this cluster, then I'll allot points to this cluster. So how am I doing it? I'm calculating the distance. So I'm calculating this distance, and then I'm calculating this distance, and then I'm seeing which is smaller or minimum. So whichever is minimum, I will allot that pixel to that cluster. So the same thing I have written over here. So now this is a small function which is doing this thing. So rnk will be 1 if k is equal to argmin. So argmin will give you minimum of xn minus mu k the whole square. So let me show you what is this. So this is my mean 1, mu 1. So here k is equal to 1, and this is my mean 2, mean 2. Here k is, so I have two means, k is equal to 2. So this is mu1 and this is mu2, two means. So what am I doing? This is the formula of Euclidean distance. So I am taking the first sample, this is my first sample, say xn, and I am calculating the mean. So xn minus xn minus mu1, that is what I am finding, square, so the square of this distance, and this I am storing. So suppose this distance is say some, say 2, this is some 2, and this distance from here to here is some, say 4. So now I have to calculate just the minimum of 2 comma 4. And remember, I don't need these values 2 and 4. What I need is in the index. So is it to the first cluster or is it to the second cluster? That is what I need. Hence the name argmax. So arg will give you these indexes. It will not give you the numbers what we want. So that will be the value of k assigned to that particular thing. So for this sample, my rn, so let me consider this is the first sample, so n is equal to 1. Please note that n is denoting the number of the samples. It is pointing the samples of the data, and k is denoting the cluster. So the first sample r1 1, so r11 means it belongs to this particular value. This r1 will be 1 because k is minimum for 1. So r11 will be 1, and r12 will be 0 because I have written otherwise, 0 otherwise. So this is assigning a sample to the cluster, given cluster. That is what this is doing, right? So by this I define this rnk over here. So this rnk will go for every sample, and it will assign 1 or 0 to this particular function, and we will get the samples differentiated. So let me just quickly so this sample, if you see, this sample will have distance less, and here the distance will be more. So I am assigning this to also this will be assigned to this will be assigned. So say I put this over here also. So if you see, so what happens is basically there is a line like this. So there will be a line that will divide both the clusters like this. So this is what will be formed while doing this particular thing, because it is just geometry. The distance of every sample is divided by a straight line, which is just the perpendicular bisector of the distance between the two. This is simple geometry. Right, now what I have to do is I have to define a cost. So this is not the right way to cluster, right? This is clustering these samples as 1 and these samples as 2. This is not the right way to cluster. So what we are doing is we are defining something as a cost. So that is, what is the cost of this particular thing. So here what I am doing is I am adding all the distances. So this distance I am adding, plus this distance I am adding, plus this, plus this, plus this. So for every sample which is belong to this particular mean, I am adding all the distance. Similarly, I am adding all the distance of these samples which are close to this, and I am calculating how much is that cost. So addition of all these, how much is it? So the same formula, it is written in formula. So for k is equal to 1 to number of k. Also please note that this is my small k. So small k is pointing 1 2, it is a pointer that is pointing, and capital K are the total number of K's. And what is K? K is the number of clusters that I'm going to use. And R and K will tell you which point belongs to which mean. So for this, since this is 1, so this will become 1 and this distance will be calculated. And for this will be R12 is 0, so hence there will be a 0 and this distance will not be calculated. So this all these distances are what I am adding, and all these distances are what I am adding, and defining a cost. Now this cost is what I have to minimize. I have to have a cost which is the minimum, because if you see, if my x say comes over here, both the means come over here, so the distance added will be very less, and here also the distance added will be very less. So I have to minimize this cost by something. So here I have chosen R and K. I have chosen which sample belongs to which mean. So what next unknown is my mu k. So now with respect to this data, I recalculate my mean. With respect to this new cluster that I have formed, I recalculate my mean. So for that, what will have, so I need a formula. How do I recalculate the mean, right? So for that, what we are doing is we are minimizing this function. So we have minimized we or maximized so many things till now. So the same procedure we are going to follow. We are going to differentiate j with respect to our mu k, because mu k is a variable over here, because I have already assigned the samples, and now the thing that I have to do is change my mu k. So this is an iterative process. Here I will assign change, assign change, assign change. That is what is going to happen. So we'll visualize how it is happening. So let us first see the formula. How do I calculate the mean? So here I have differentiated it. So you can see R and K is as it is, xn is as it is, minus mu k. So this whole square, the 2 will come out and there will be a minus sign because of this. And this thing will set equal to 0. Also please remember, here the summation is gone because I am doing this differentiation for each value of k. So it is like I am differentiating this function with 1 mu1, and then I am differentiated with respect to mu2. Also please remember, I am choosing mu1 as a variable over here because this is going to change now. This is not the right mean. In the second iteration I'll have to change this. So this is what I've done. Now when I equate this to 0, this 2 will go, dividing by minus 2. So this 0 kills the 2, and I've separated these. So next, when you see, I took this term over there and I got this. Now mu k does not depend on n, so mu k will come out. Please note, this is my small k, and this particular thing will come down. So let us see what this equation represents. So this equation represents Rnkxn. So Rnkxn is what? Say for this particular value, Rnk. So R11 is 1 and xn is this value. So there will be this xn, and R12 is 0 for this. So this will not be allotted to this. This is just allotted to this. So what this equation is meaning is, actually you take all the samples that are belonging to one mean. R and K is all the samples that is belonging to one mean. These are all samples upon the total number of samples that are belong to that mean. So what it is essentially telling is, you take the mean of all these samples, just the normal mean of these samples. That is how you will figure out the new value of mu k. So let me write this, say the new value of mu k for the next iteration is just going to be the mean of these things. That's all. Similarly, the new value of mu2 is going to be the mean of these things. The normal mean of these things is what is going to be. So if suppose by intuition, if say there are a lot of samples over here and a few here, so the new allocated mean will come somewhere over here. So please understand, the mean will try to be in the center of the whole data. So here I'm just assuming that the new mean on the next iteration will come over here. Similarly, the new mean, say in this iteration, comes over here. So there was a lot of crowd over here, so the new mean came over here. So now this is going to be the new mean, and now you again go to step number 2 and again calculate for this new mean which sample will belong to this mean. You take the difference. So let us do that. So now that we have our means over here, say one of the mean is here. So this mean is what I am writing over here, that I've calculated in my previous iteration, and this mean is over here. Now the same process, what I'm going to do is I'm going to say this was my first pixel, so I'm going to calculate the distance of this pixel from this mean, and then the distance of this pixel from this mean, and take the minimum. So you can see that this is the minimum, so this will be allocated to this. So like this we'll decide the values of r and k. So here you can see r and k values are coming into role. So all these points distance are less for this particular thing, so I'm making them black. So all these points have become black because they belong to this. Now you can see say this particular point no, okay, chalo, this point is quite close to this, so let these pixels be over here, and this pixel will be allotted to this. Oh sorry, this is white. So this is the second iteration. So you can see in the second iteration we have almost clustered the data. We have got this particular data as black, all black. So this is one of the clusters, and this is one of the clusters. Now in the next iteration, this data's mean will get calculated. So what you have to do is you have to calculate the mean of this data. So you can see the mean of this data will be somewhere in the middle. The mean of this data is somewhere in the middle. So I am calculating mean from the data, right? So there will be somewhere in the middle for this cluster, and will be somewhere in the middle for this cluster. So now I have got my almost accurate position of my mean, and I have successfully done my k-means clustering. Also, I am again repeating, this is just one class. This is still sunflower data. The classes have not changed. This is data of the one class only. Just that now what we have done is, instead of doing this, instead of just using one circle for every the whole data, we have done this, which is giving a good, better approximate is what we are doing over here. And this is all about k-means algorithm. So this is the algorithm that I performed over here. So I hope that you understood this, but still I'll give you a good right visual representation now, so that will make things more clear. So let us see that. Right. So here you can see initially I have assigned this mean and this mean. So this was my first step. I am assigning randomly the means, and this is my data. Okay, this is the data to be clustered. So remember, this is just one class data. This is to be clustered. So what I'm going to do is I'm going to calculate the distance of this pixel with this mean, calculate the distance of this pixel with this mean, and then going to see which is minimum. So accordingly, I'll do it for every case, and I will see like this, something like this will happen. So remember I mentioned that there will be a line, a discriminator that will be formed, and that will be just a perpendicular bisector of the line joining these means. So this is what is happening, because here this is the case because I'm just considering the mean. Here there is no notion of variance, there is no notion of any Gaussian or something. I'm just calculating the distance, and then I'm assigning whichever is having small distance, I'm assigning that. So this is what happens. Then these data get fall into this mean, and this data falls to this mean. Next, now what I'm going to do is I'm going to take the mean of this data, and then I'm going to take the mean of this data and get the new mean. So you can see somewhat like this happens. So this data's mean comes say over here, and this data's mean comes somewhere over here. So see, this is what happens. Next, what we are going to do is we are going to again calculate the distance of every pixel from the mean, and we are going to again allocate the minimum. So suppose this pixel, so I'm again going to calculate the distance of this pixel from this mean, and then this pixel and this mean, and going to take the minimum. Whichever is the minimum, that will fall in that cluster. So you can see something like this happens. So again there will be a line formed that will be perpendicular bisector of the midpoint of the line joining the two means, and we get like this. So you can see a quite good amount of data is already clustered in the second iteration. So that is the beauty of this algorithm. Next, what is going to happen is we'll take the mean of this new data. So we'll just take the mean of this data, and we find out that it will come somewhere over here, and we'll take the mean of this data, so it will come somewhere over here. So this is what we have got. So I guess this is the actual mean of this center point of this data and the actual mean of the center point of this data. Visually you can guess that. Again, it is going to classify both of them, and now you see that this will not change more, because now you again calculate the distance, this pixel from this, and then this pixel for this, like that for every pixel, and you'll find out that more or less the graph will remain similar. So as soon as you get something like this, that the means are not changing, you can stop your algorithm over there. Or the other case is that do a particular number of iterations, say 10 iterations or 20 iterations. If it does not look similar after 10 iterations also, then you can stop it there. So that is what you can do. So you can see the mean did not shift a lot, and this is what is the final output that we get. So how beautifully you can see the k-means algorithm has clustered the data. And that was all about the k-means clustering. In my next video, we are going to see the Gaussian mixture model, which is a more general case of k-means clustering. So in that, we are going to see the variance also comes into picture. We are going to actually fit the Gaussians, and we'll see all of those beautiful things. Thank you so much for watching my video. Thank you.